random for the June examination 2025 for grade 12 physical sciences, paper 1. So this was a 3-hour paper with marks of 150. The paper was to be done in 3 hours. So we have 15 pages, okay, and 3 data pages. We're dealing with 9 questions, okay, that we shall have to work on. So let's see how we should have fared within this paper. So question 1, which is always the multiple choice, they're telling us that we have various options as possible answers, but each has just one correct answer. You just need to choose the correct option. Okay, 1.1. Which of the following forces will always act perpendicular to the surface on which the body is placed? So that is option C, which is the normal force. Okay, tension, friction, gravitational do not apply. So number 1.1 is C. And then 1.2, we are being told that a car of mass m moves along a straight line at a constant velocity v in the easterly direction. The velocity of the car decreases to 1/3 of the original speed in t seconds, okay, as shown. And then they telling us that it is not drawn to scale. And then the question is asking for the change in momentum of the car. And so one thing you know about the change in momentum is that it is mass multiplied by the v final minus the v initial, okay? So our mass is m. Our v final is 1/3v, and then we are subtracting the v initial, which is just a v. When we simplify this, okay, our m is gonna be 1/3 minus 1. That's gonna be -2/3, okay, -2/3, but v. Meaning that the overall change in momentum is going to be -2/3v. Now, since the initial direction was easterly, okay, the negative aspect simply indicates the opposite direction. So meaning that our change in momentum will be within the west, okay? So 2/3v, but west. 2/3, we're talking of mv, okay, because we don't have the value of mv. So 2/3 mv west, which is option D. All right, then 1.3. An object Y exerts a gravitational force of 1,000 newtons on object Z when the distance between the two objects is r, okay? The two objects have a mass of m each. Which of the following will increase the force to 4,000? Okay, so initially the force was 1,000, and now we're going to have 4,000, which means we're focusing on 4F. So for us to increase the force, the distance need to be halved. Okay, so which means it will be like r²/4 to give us 4. So half the distance, so half the distance between the centers, which is option B. Then 1.4, we're being told that a ball is kicked across the floor and it comes to a standstill after t seconds, okay? Which of the following statements describes the total mechanical energy and the net work done on the ball? Okay, so the first one, total mechanical energy, one thing we know is that for as long as the ball is rolling, we know that the floor is rough, and because of the presence of friction force, the ball will come to a standstill, okay? Now, the kinetic energy will decrease because the final velocity is a 0. And then the potential energy might stay the same, okay? But now, when the ball is rolling, we know that the combination of kinetic energy and the potential energy is going to be bigger than the potential energy only at the end when it is rested, okay? So in that case, the fact that there's a difference between the energies or the mechanical energy, so you're gonna choose not conserved, okay? Then the work that's gonna be done, the net work done, only force that is acting on this ball to bring it to rest is just the frictional force. And friction always works in the opposite direction. So I'm gonna go for negative, which is option A. And then 1.5 are telling us that a crate is given an initial velocity and it slides up a frictionless incline until it comes to a stop. Which of the following graphs shows the correct relationship between the kinetic energy and the potential energy? So we know that when the crate is sliding up, okay, the moment it stops, at that point, the EK is going to be 0. So in other words, with the graphs that we're looking at, we should be focusing on the EK being a 0 at the end of the graph. So B is out, D is also out. Then as this one is a 0, the body will only have what we call the EP max. Okay, the maximum potential energy is what will be left. But initially, the potential energy was a 0. So when I look at A and C, these seem to be the best options. But is there friction? They are telling us up a frictionless. So if it is frictionless, then I'll choose option C. Okay, if there was friction, then option A would make more sense. Then 1.6, for a light redshift indicates that the light source is moving away from the observer. So option A is going to be the best there. And then 1.7, 2-point charges, 7 nanocoulomb and negative 5 nanocoulomb are brought together up until they touch. Immediately after, they are returned to their original position. So one thing we know is that when charges are brought together, after the separation, the charges must have equal magnitude, okay? So a 7 minus a 5 is going to give us a 2. You divide by 2, meaning that we're going to have a nanocoulomb on each of the spheres, okay? Now, since these nanocoulomb are positive, okay, the charge is positive, we expect a repulsion. So option C is out, option D is also out because the field lines are crossing each other, and of which they shouldn't. Option A and B, since they are positive, the field lines should be moving outwards and not getting into the sphere. So option B becomes the best option there. Then 1.8, a non-ohmic conductor can be described as a resistor for which. So we know that ohmic obeys Ohm's law. Okay, non-ohmic does not obey. Okay, so Ohm's law is valid. So this is out for a non-ohmic. Current potential difference produces a straight line. This is for ohmic. The resistance does not vary with a change in temperature. Well, with ohmic conductors, we remember Ohm's law. Normally it talks about the temperature being what? Being constant. So if the temperature increases, even the resistance will definitely change, whether it is ohmic or non-ohmic. So option D, the resistance is not constant, okay, and then it varies with the applied potential. So option D would be the best for me, okay? And then 1.9, 4 identical resistors are connected as shown, which connection will result in a total resistance of 4 ohms. Let's see, resistor by resistor, okay, option by option. So here we have 2 series, okay, meaning that when we plus the top, we're going to have a 4, and then we're going to have a 4. Then these 2 will be in parallel, okay? So for me to get the effective for the parallel, it will be 1/4 plus 1/4, which will give us a 2/4, meaning that the effective resistance is just a 2. Alternatively, use the product over the sum, meaning that it is 4 times 4 over 4 plus 4. So 16/8, which is 2. So this is out. Let's look at this one. We have a 2 and a 2, so these ones are in parallel. Let's start with this. So you're going to have the product over the sum, 2 by 2 over 2 plus 2, which gives us just a 1. Then if that's a 1, plus 2, that is 3, plus 2, which gives us a 5 ohm. Okay, let's look at the next one. With this one, we know that these 2 and these are in series. Ne? So technically, there is no difference between option B and option C. the way I'm looking at it. The way I'm looking at it. But let's see. Let me pause on this one. Let's try option D. So 2, 2, and 2, that's going to be 1 over 2 plus 1 over 2 plus 1 over 2, which gives us 3 over 2. Then the actual resistance, okay, is going to be 2 over 3. And then when you plus the 2, that's going to be 6 plus 2, that's going to be 8 over 3, which is not a 4. Then this one, for me, I believe it's more like the same as this. Okay, so if I take it to be the same as that, but I've already taken out A, I've already taken out B, and then I've taken out D. So I'm only left with this option C. I'll go with C for the sake of just choosing an option. Okay, but I wouldn't also agree with C, but I'll take it for the sake of just choosing an answer. Then 1.10, they're telling us that a kilowatt hour refers to the use of electrical appliances. Nope. The power of electrical appliances. Nope. 1 kilowatt of electricity used for 1 hour. Very correct. So 10 is going to be a C. And then question number 2. A person pulls a block of mass 12 kgs to the right using a light inextensible rope T. The block is pulled from point A to B at an angle of 40 between the rope and the horizontal surface. The coefficient of kinetic friction is 0.31, and the block is pulled at a constant velocity of 10. Okay, so meaning the acceleration is 0. Okay, then the first question, define the term kinetic frictional force. So we know that kinetic frictional force is just the resistance force. Okay, let me just call it resistance force or resistive force that is acting. Resistance force doesn't sound proper. Resistive. Okay, resistive force that is acting between, okay, we can say between two surfaces, acting between two surfaces in contact. So the surfaces need to be in contact and then they have to be moving, okay, when they move relative to each other, relative to each other or relative to one another. Okay, so there has to be motion for us to have the kinetic friction force. Then 2.2, they want us to draw a body diagram of all the forces that are acting on the 12 kg. So number one, we have this tension. Then we have the frictional force, Fk. Then we're going to have the normal force, Fn. And then we're going to have the weight downwards. So for me to draw the free body, 2.2, let me put it this side and say 2.2, 2.2. Okay, so this, we say the tension is at an angle. The weight is, what's happening? Why am I writing skew? My book is Q. So something like that. And then we say the frictional force is going to be the Fk, and then we're going to have the normal force, Fn. All right, and then 2.3, they want us to get the magnitude of the tension. So when we look at the tension, we have two components. Number one, we have the vertical component, which is going to be T, the sine of 40, and then the horizontal, which is T, the cos of 40. Now, if I look at just the horizontal, I'll be focusing on this being equivalent to the frictional force. Okay, so I'll say that F net is equal to MA since it's moving, but we say that we're going to have a 0 this side since it's moving at a constant what? Velocity. So our T, cos of 40, okay, T cos of 40 plus a negative Fk should give us a 0. So T cos of 40, we know that frictional force will be given as mu multiplied by the normal reaction, okay? So that is mu K multiplied by n. But our normal force is going to be affected, okay, because it has the T sign included, okay? The T sign is part of our normal force, which is, so we're gonna get the weight, and then we subtract this whole T sign of 40, and then we're good to go. So I'll say that T cos of 40 minus the mu K into my mg minus T, the sine of 40, should give us a 0. Okay, let's just substitute, and as we open up, so T cos of 40 minus the mu, which is 0.31, into the mass is 12 times 9.8 minus T, the sine of 40 should give us a 0. Okay, so when we open this up, it's T cos of 40. But why don't I simplify cos of 40 once? Okay, so from our calculators, what is the cos of 40? That is 0.766. Is that correct? We're saying the cos of 40 is 0.766t minus, when I multiply this entire thing, okay, 0.31 times 9.8 multiplied by 12 is giving me a 36.456. 36.456, this and that, I'm going to get a plus. What is the sine of 40? Sine of 40 is 0.643t is equal to 0. Then I need to add this and that. Okay, so when I get that answer of mine, and then I plus the 0.766, I end up with a 1.4087, which is a 409, is equivalent to 36.456. Then I'll divide both sides. Okay, there's a t there. Divide by 1.409, 1.409. Then what is t giving us? What is t giving us? Why am I having? Someone says our answer is kind of not right. It's fine. What did we do wrong? We did not multiply by the 0.31. Multiply this by the 0.31. Thank you very much. So 0.643 times 0.31, which is 0, so this is a 0.766t plus 0.199t. Okay, when you simplify that, what do we end up with? We're gonna have 766, which is a 0.965, 0.965t. So instead of us dividing both sides by 1.4, we're just gonna divide. So it's a 36.456 divided by 0.965, and this gives me an answer of a 37.78 newtons. Okay, so this is out. Okay, so that is what we had to do for the, have we answered the question for the tension? Yes. Then 2.4, they are telling us that the block is moved a distance of 24 meters, okay, from there up to there. Calculate the time it will take. So we know that speed is given as distance over time, and then we're looking for the time, meaning that our delta t should be the displacement divided by the velocity, or the change in the velocity itself. Okay, so that's going to be a 24 divided by 10, which gives us 2.4 seconds. Okay, then 2.4.2. If the block's velocity is now increased to 20 meters per second, how will the frictional force be affected? I mean, increasing the velocity has no effect on the friction. The friction will basically stay the same. So we're going to say it remains the same. Okay, then 2.5. The angle between the rope and the horizontal is increased to a 50. Okay. What will be the effect on the kinetic frictional force acting on the block? Now, initially it is horizontal. When it is horizontal, all the normal force will be equivalent to the weight. Is that true? No. It's not horizontal. We're looking at a 40. Okay. But now we're saying that we are increasing it to a 15. Okay. So let's see. Between the cos of 40 and the cos of 50, which one is bigger? So cos of 40 is 0.766. And then the cos of 50 is 0.64, meaning that increasing the angle, okay, will decrease the normal reaction. And if the normal reaction is decreased, meaning that the frictional force will also decrease. So this is going to be a decrease. Explanation is that increase in the angle, okay, will lead to the decrease in the normal force, hence the frictional force will also decrease. Okay, so that is the explanation that we could be having. Question number 3, a rocket of total mass m is launched from the surface of the Earth. The initial weight, remember we're talking about weight, is 5.38 times 10 to the 6 newtons. The mass of the rocket decreases due to the loss of fuel that is used to propel the rocket. When the distance between the center of the rocket and the surface of the Earth is 9,000 meters, the rocket experiences a gravitational force of this much. Okay, the diagram below is not drawn to scale. That's what we have. And then they ask us to state Newton's law of universal gravitation. So we know that for any two bodies, okay, in space or in the universe, okay, they experience, or each body, because we can say that each body experiences or exerts a force that is directly proportional, okay, that is directly proportional to the product of the magnitude of the masses, okay, and inversely proportional. So inversely proportional to the square of distance, of the square of the distance between them or between the centers. So something of the sort. Then 3.2.1, they want us to get the total mass of the rocket before it is launched. Now, the question gave us the weight, okay? They want us to get the mass. So we know that weight is given as mass times gravity. So for us to get the mass, we shall get the weight divided by the g, meaning that we shall get our 5.38 times 10 to the 6, and then we divide it by the 9.8. So 5.38 times 10 to the 6, we're dividing it by 9.8. This gives us 548,979.59. This is going to be kilograms. All right, then we move on. That is 3.2.1. Then 3.2.2, they want us to get the mass of the rocket when it is 9,000 meters away from the surface of the Earth. So we need to use the universal gravitational force. So we know that that is given as F being the same as G, M1, M2 divided by the R squared, okay? So we were given the force as, what's gonna be the force? Because now if the force is acting here, and this is our distance to the center, but then they told us when it is 9,000, meaning that we need to add the radius of the Earth. So 5,04 times 10 to the 6. So I'll say 5,04 times 10 to the 6 should be equivalent to 6,67 times 10 to the negative 11. Then we know that the mass of the Earth, okay, mass of the Earth is given as 5,98 times 10 to the 24 multiplied by the mass of the rocket, which we don't know. And then we are dividing this by the 9,000 plus the radius of the Earth, which is 6,28 times 10 to the 6 squared. Okay, so that's what I have. Then I just need to do the cross multiplication, meaning that the mass of the rocket is going to be 5,04 times 10 to the 6 multiplied by the 9,000 plus 6,28 times 10 to the 6 squared. And then I'll divide this by 6,67 times 10, that. Okay, times 10 to the 24. So the answer that I'm getting, maybe I should just round it off and give it in a scientific notation. So it's 5,16 times 10 to the 6 kilograms. This one, we can also write it in that same form, okay? Meaning that it will be 5,49 times 10, 1, 2, 3, 4, 5 kilograms. Okay, then the next question. They want us to get the mass of the fuel that was consumed. So for us to get the mass of the fuel, we're going to get the answer in 3.2.1, subtract the answer in 3.2.2, and get our answer for the mass of the fuel that was consumed. So we're saying 3.2.3. So mass of the fuel is going to be the initial mass, which was 5,49. Okay, that's 5,49 times 10 to the 5. We are subtracting 5,16 times 10. Does it make sense though? This is to the 6. Okay, so when I tried to subtract this looks impossible. So there's something I might have messed up somewhere, somehow. So I'll just go back here. This is supposed to be a 3.8. Okay, so when I punch that, I'll get my answer, but this is supposed to be a 5 as well. So meaning that it is a 5. This is also, is it a 5,49? Is that what we got here? Yes, 5,49. Now it's fine if the exponents are both the same and it makes life easy. So 5,49, we are subtracting 5,16, meaning that we have a 0,33. And then when we multiply it by 10 to the 5, we're getting 33 of fuel, okay? Or 3,3 times 10 to the 4. So that is how I would have approached that question for 2 marks. Then 3.3. 3.3, they are telling us that the rocket is on its way straight to the moon, okay? So as the rocket is moving to the moon, it simply means that the distance between the Earth and the rocket is increasing, while the distance between the rocket and the moon becomes smaller, okay? So what will happen to the gravitational force between the moon and the rocket as the distance increases? So the explanation here is going to be as the distance decreases, the distance decreases, the force must increase. Okay, increase would be the best option for that part. Then question number 4. Okay, question number 4. They're telling us that a hot air balloon moves upwards at a constant velocity when a block B is dropped from the side of the balloon and falls to the ground. The balloon is 50 meters above the ground when the object is dropped. The graphs below show the motion of both the balloon and the block, and then the graphs are not to scale, ignore. So upwards, positive, no calculations. It's not really a big deal there. Then velocity time graph for this, we have 5, we have V. So I'm assuming T2 is when the block hits the ground. Okay, I'm just assuming because it's not telling us anything of the sort. Then which of the two, the hot air balloon or the block, is in free fall? So I'm going to say it's block B. Okay. Why is it block B? Because we know that this hot air balloon moves up at a constant velocity. Okay. Then when you look at the block is just dropped. Okay. When it is dropped, it's like there's no initial velocity to it. So block B will be under the free fall. And what is the reason? We're going to say that its motion, okay, its motion is entirely under the influence of G, influence of the acceleration due to gravity only. Then 4.2, can we use only the equations of motion to calculate the following values? Number one, they want us to get the size of T1 or the time T1. Now we know that T1, because this is the motion of the block, we're seeing that the initial velocity, the final velocity is 0 here. One thing we need to remember is that when objects are thrown from a hot air balloon, okay, they will momentarily take on the inertia principle, whereby they will continue moving with a 5 meters per second upwards up until they reach a maximum and then they drop, especially for this block in particular or in question. So we know that our V initial is going to be 5 meters per second, but we're saying that our V final is a 0. So meaning that at T1, that's when block B reaches the maximum height, okay? So you're gonna say V final is equal to V initial plus A delta T. Okay, let's start by the equation or the formula, and then we do the substitution. So our V final is a 0. Our V initial is a 5. Okay, and then plus, since it's moving upwards, gonna be negative 9,8 multiplied by T. Okay, then you transpose that, meaning that the 9,8T should give us a 5, then divide both sides by 9,8, and then 9,8, meaning that our T becomes 0,51 seconds. All right, so if that is 0,51 seconds, what's the next question? They want us to get the velocity of block B. Velocity V of block B. So velocity V is more like the final velocity when the block hits the ground. So what I'm going to do here, I can use the VF squared, that formula, and say VF squared is equal to V initial squared plus 2A delta. In this case, we can say delta Y or delta X. Then let's do the substitution. We're looking for V final squared. So VF squared is equal to the initial, which was a 5, né? So that's going to be 5 squared plus 2 multiplied by the negative 9,8, and then the displacement is also going to be negative 50. So VF squared gives me 1005. And then when I find the square root of that, I'll end up with a 31,7, but that is meters per second. So V is a 31,7 meters per second. Then they want us to get the time T with which the block hits the ground, time taken to hit the ground. Okay, so with that, I'll use the delta Y is equal to V initial delta T plus a half A delta T squared. Let's do the substitution. So it's going to be a negative 50. Our initial is a 5 and T. This is going to be plus a half negative 9,8 and then T squared. Okay, then when I do the magic, that's going to be 4,9 T squared minus 5T minus 50 is equal to 0. If we use our quadratic formula, negative b plus minus square root of b squared minus 4ac over 2a, what do we get here? Let's see, 4,9. Minus 50. So I'm getting two answers, negative 2,72 seconds. Oh, it's going to be a 3,75 seconds. So we know that time can never be negative. Ne? So in this case, our t of interest is going to be at 3,75 seconds. Okay, then we move on to 4.3. They want us to sketch a position time graph of block B from the moment it is dropped up until it reaches the ground, okay? Using the ground as a reference of 0. We need the initial height, the time taken at the maximum, and then the time. Okay, so I'll have this. So this is my delta y in meters. This is my time in seconds for 5 max. Ne? Okay, so initially, this block was dropped at 50. Okay, then it went up momentarily, reached the maximum, and then came down. So the time when it reaches the ground here, the t we are saying is a 3,75 seconds. Okay, that's the position 0. Then when it reaches the maximum, that's our t1, which is the 0,51. So basically, that's what the question wanted. So the 50, the maximum, and all of that. They say the time. They don't want the maximum height, just the time. Okay, so that is 4.3. Then question number 5. Question number 5, we have a vector diagrams below that show the momentums of car A of this mass, which is traveling to the right before and after collisions with the stationary car B. The collision lasted for a period of a half of a second. And then after the collision, car B moves to the right with a speed of 20 meters per second. Okay. Calculate or state the principle of conservation of linear momentum. So we know that in an isolated system, we know that the total linear momentum is conserved or remains constant. In an isolated system, the total linear momentum remains constant or remains the same. 5.2.1, they want us to calculate the velocity of car A before the collision. So what we have is the momentum, okay? And we know that momentum is given as the mass multiplied by the velocity. So we know the mass of A. So it's just going to be 30,000, okay, divided by the mass, which is 2,000, which gives us 15 meters per second. Okay, so that is 15 meters per second. And then they want us to get the mass of B. So here we can apply the conservation. Okay, we apply the conservation of the momentum. So meaning that we're going to have, so mass of A, V initial of A, plus mass of B, V initial of B should give us the mass of A, V final of A, plus the mass of B, V final of B. Here we have the momentum already, so there is no need of calculating that. So we're just going to say 30,000. Okay, so that's a 30,000. Plus, it was at rest, so that is a 0. The final momentum is 10,000, okay, in the same direction. And then the final here is going to be mass multiplied by the 20, since they told us that the body is moving at 20 meters per second. So let's move this 10,000 to that side, meaning that we're going to have a 20,000 divided by 20. So this gives me 1,000 kilograms. All right, then 5.3, they want us to draw a labeled vector diagram showing the magnitude and direction for the change in momentum. So we know that change in momentum is the mass, or we can say momentum final minus momentum initial. So it's the 10,000 minus that was at 30,000. Meaning that we're going to have change in momentum of negative 20,000. So the 20,000 is acting in the opposite direction, which is the left. So we're going to have something like that. So this is 20,000 kilogram meters per second. Okay, then 5.4, can we calculate the magnitude of the net force that the car exerts on car B? So we know that F net is the same as the rate of change in momentum, okay? So our F net, because the formula says F net delta T should give us the change in momentum, the impulse, okay? Then for us to get the F net, we have our change in momentum, which we said is a negative 20,000 over the change in time, which is 0.5. So this gives us a negative 40,000. So it's going to be, but they said A, magnitude of the net force that A exerts on B. Okay, so that is the answer that we have. Then 5.5, use the impulse momentum theorem to explain how the airbag. Okay, now we know that the change in momentum must give us F net delta T. Okay, this is the impulse, and then that is the change in momentum and all of that. So one thing that happens, okay, with the airbags of cars is that the aim is to basically increase the time of contact between the airbag and the driver so that the force will definitely decrease. So to reduce, okay, the force, we're saying that there is need to increase the time, okay, over which the momentum changes, over which the momentum changes. So increase in the time will lead to a decrease in the force. You can even write this kind of expression whereby the F net is inversely proportional to delta T. Okay, something like that. Then question number 6. Question number 6, is that the correct part? This is 11. This is 12. Okay. Question number 6, they're telling us that a 20 kilogram kg box initially at rest at point Y on a rough horizontal surface. The box is pulled to the right by a constant force parallel to the surface, and then the box is moved the horizontal distance 4 meters, and it experiences a frictional force of 65 newtons. Can we define the term the non-conservative force? So we're saying this is a force, okay, is a force in which the work done, okay, force in which the work done by the force depends on the path taken, depends on the path that is taken. They name the non-conservative force or forces that are acting on the 20 kg. So we have the 100, which is the 100 newtons, or we can also have what we call the frictional force. Okay, so this is applied force. Let's call it applied force, the 100. And then we also have the frictional force. And then 6.3, using energy principles only, can we determine the speed of the box at Z? Now, what I can do, or what I'll look at, I know that the net work done is equivalent to the change in kinetic energy, okay? So this box is having frictional force in that direction. We have the applied force. So it's only two forces that are acting on this body. So for me to get the network, I'll get the work done by the applied force and then the work done by the frictional force, and then I'll equate it to the change in the momentum, or sorry, the change in the kinetic energy for both of them. So let me come this side and say that this is 6.3. Okay, 6.3, we're saying W net is equal to the change in EK. So we say the work done by the applied force plus the work done by the frictional force should give us the change in the EK. So the applied force is 100 multiplied, because we know that the work is force delta X cos of theta. Ne? So 100 multiplied by 4, the cos of 0, plus the 65 multiplied by 4, the cos of 180 should give us a half the mass. Okay, the mass is 20. Okay, so that's 20 into the V final squared minus the V initial squared, which is a 0. So this is going to be a 400. Okay, then 65 times 4 gives me a negative 260 is equivalent to 10 VF squared. So 400 minus 260 gives me 140. I'm dividing it by 10, and then I'm finding the square root for me to get my V final. So square root of 14 is 3,74. So that's what I'm getting, 3,74 meters per second. Okay, then 6.4, can we calculate the average power that is dissipated by the 100 Newton force between Y and Z? So we know that the power average is given as the force multiplied by the velocity. Our force is 100, okay, and the change in velocity is going to be the 3,74, okay, minus the 0, the initial, which is 3,74 here. Okay, the change in velocity is 3,74, meaning that we're going to have a 374 power is given in watts. Okay, then 6.5. The box is now pulled upwards by 100 Newton force on an original surface, which is now at an incline with an angle that we don't know. Can we draw labeled free body diagram showing the conservative? The first question was the non-conservative. Now we're talking about the conservative. So we're going to have one, the weight, and then we're going to have the normal force. So we're just going to say weight, and then we're going to have the Fn. So those are the two forces for 2 marks. Then 6.5, will the box still have the same speed after the 4 minutes? Or the 4 meters, as in question 6.3, right? Only yes or no, and so on. Now, when we look at the incline is going to present two components of the gravitational, of the weight, and of which our frictional force depends on this component, the mg cos of theta. Okay, so instead of it depending on the entire weight, it's just depending on a component, just a portion of it. So meaning that the frictional force is going to decrease. So will the box have the same speed and what? So if the frictional force decreases, meaning that the distance that this object can move is going to be more than 4 or equal to 4. Will it still have the same speed after the 4 meters? Wait, will the box still have the same speed after 4 meters as in question that? So the answer is going to be a yes for me. Okay. The reason is going to be there is less friction. It's a yes because the friction has decreased. So if the friction decreases, meaning that it can even move at a greater distance. Okay, then question number 7, a hawk emits a sound at a frequency of 90 hertz. The speed of sound is 340. Can we state Doppler effect in words? So we know that Doppler effect is basically the apparent change, okay, in the frequencies observed and emitted. Okay, we can say it's the change. Okay, the change in the frequency detected by the observer, the change in the frequency detected by the observer, okay, when there is relative motion between the source, the observer, between the source and observer, okay, between the source and observer in a medium, in a wave medium or in a medium, something of the sort. So for as long as you talk about the apparent change within the frequencies, the observed frequency and the emitted frequency, as a result or because of the change in the velocities of the source and the observer. Then 7.2, a stationary observer will get 88 hertz. Is the hawk flying towards or away? The answer is that it is flying away, because when it flies away, the frequency is smaller than the emitted one. Then calculate the speed of the hawk. So from our, this is going to be 7.3. And then 7.3. What is going on here? Okay, let's try this side. 7.3, so from the formula of Doppler, we know that V plus minus VL over V plus minus Vs multiplied by the frequency of the source. So what's going to happen then is that we already have our velocity of the listener, okay, which is 0. Velocity of the source is what we need. The V is a 340. Frequency of the source was a 90. Frequency of the listener is 88. Now, since the hawk is moving away, meaning that our frequency of the listener is V minus VL over V plus Vs times Fs. This is what we're going to use. So the listener is 88. This 340 minus 0 over 340 plus Vs times 19. Let's do the cross multiplication or the switching. That's going to be 340 times 90 over 88 is equal to 340 plus Vs. Okay, so when I punch this in the calculator, we have 340 times 90 divided by 88. It gives me 347. 727272. So when I subtract the 340, meaning that our Vs is just 7,2. What am I saying? Because 347,72. So it's going to be 7,72 meters per second. But 27, which means it's a 73. So 73 meters per second. So that is what we would have done with question number 7. Question 8, 3-point charges A, B, C placed in diagram as shown below. Can we state Coulomb's law in words? So these laws we need to know. We need to remember how to state, because these are just a giveaway. Okay. So if we have 2-point charges, or if we have 2 charges in space, we're saying that the force, the electrostatic force, okay, we normally say the electrostatic force between them is directly proportional, okay, directly proportional to the product, okay, of the magnitude of the charges, okay, and inversely proportional to the square of the distance between them. So something like that, for as long as you know how to, Q1, Q2 over R squared. It's just putting this in words. Then 8.2, they want us, they don't want us. They're telling us that the net force on A due to B and C is 0,866. Can we calculate the distance D as indicated in the sketch for 5 marks? Okay, so we need to get the force FC, the force AB. Okay, so let me just start with it here. So with our FAB, it's going to be K. Okay, let me put this side because I don't have space there. We're saying FAB is K Q1 Q2 over R squared. So 9 times 10 to the 9. The Q1, which is the A, is going to be 5 times 10 to the negative 6. This one is 2 times 10 to the negative 6 divided by the distance, which is 0.5 squared. Okay, when I punch that into the calculator, what are we getting? So this gives me 0.36 newtons, okay? Then the FAC is going to be the same. It's going to be a K Q1 Q2 over R squared, which is 9 times 10 to the 9 multiplied by the 5 times 10 to the negative 6. Then this force is 7. Okay, times 10 to the negative 6. We're dividing it by d squared. Okay, so when I simplify this, I'm getting something like a 0.315 over d squared. So this is the force of AC. Then, since we're talking about the net force being 0.866, okay, I'll say that our F net is 0.866. For the three forces, we're going to have some sort of a right angle triangle. One for the vertical, because there's attraction, and then there's also attraction there. And then one for the horizontal. So the Fy, the F horizontal, and then the F vertical. So if this is 0.315 over d squared, and then this is a 0.36 squared. Let's use the theorem of Pythagoras. Okay, is it Pythagoras? Yes. We're going to use Pythagoras and then proceed to get the net force and then do the substitution as required. So we're saying that our F net should be the 0.36 squared plus the 0.315 over d squared. This should be squared. Okay, this is F net squared. Meaning that if we have the 0.866, we square this. Okay, should give us that 0.36 was direct. Okay, that's fine. Then I'm going to have this. Why don't I just subtract once so that we save time? Okay, so minus 0.36 squared must give us the 0.315 over d squared. Everything is squared. So for me to get rid of this square, I need to find square roots on either sides. Okay, so let's punch that and see. It's going to be 0.866 squared. You're subtracting 0.36 squared. I'm ending up with a 0.788. Okay, is equivalent to 0.315 over d squared. Okay, so let me transpose and switch, meaning that our d squared is going to be 0.315 over 0.788. For me to get the d alone, I must find the square root there. So the fact that we are having a lot of decimals, it might kind of affect our level of accuracy. But the answer I'm getting is 0.635, which could be rounded off to 0.64 meters. I don't know. That's what I'm ending up with. So it could be round about that range. All right, then 8.3. They are removing C, and point P is 0.2 meters to the right of B. Can we define electric field at a point? So this is basically the charge, okay, per unit area. The charge per unit area that will be experienced is the force. It's not it's charge. It's basically the force per unit area, because it will be in a charge format. So the force per unit area that is experienced at that point, at a given point. All right. Then can we draw a labeled vector diagram for the electric field of P as a result of A and B? So when you look at A and B, sorry, A and P, there's going to be attraction. So meaning that's going to be on that side. Okay. And then B and P, there's going to be repulsion, meaning that's going to be in that sort of direction. So for me to combine everything together, it should be, this is going to be the electric field of B and P. And then this side, we're going to have the electric field of A and P. All right, so that is 8.3.2. Then 8.3.3, they want us to calculate the magnitude of the net electric field at P. So one thing we know about the electric field is given as the E being equal to KQ over R squared. So if I look at the AP, first of all, it's going to be 9 times 10 to the 9. And then my A is 5 times 10 to the negative 6. Okay, 5 times 10 to the negative 6 divided by, remember we're looking at A, so it's going to be 0,5 and 0,2, which is a 0,7. So 0,7 squared. What does this give us? Gives me a very big answer. So 91836,7, I can say 3. Okay. Then let me look for the electric field as P and P, which is going to be 9 times 10 to the 9 times, in this case, we're looking at 2. Okay. Times 10 to the negative 6. And then I'm dividing it by the R squared, which is 0,2 squared. When I punch that in the calculator, I'm getting a 450,000. That is Newton per Coulomb. Then no, Newton per meter. It's Newton per meter. Okay, then since we're looking for the net, we're just going to do the subtraction. So 450 minus the 91. Okay, so 450 minus the 91, 836,73. So this gives me a rough answer of 358163,27, which is approximately 3, maybe 58 times 10 to the 5, not 8. Okay, Newton per meter. All right, then 8.3.4. If point P was now put between A and B, okay, the net electric field would never be equal to 0 at any point. Can we explain the validity? Can we explain the validity? Now, if P is removed and placed somewhere here, the fact that this is a positive charge and this is a negative charge, there's going to be a transfer of field lines, okay? We can only get a net of a 0 if the forces are sort of, if the charges are the same and there is some bit of repulsion in that manner. But in this case, the signs are opposite, which means there is an attraction force that must be always greater than 0. 8.4, the relationship between the electrostatic force and the charge is illustrated below. Okay, so this is the force F, this is the charge Q. Okay, what mathematical relationship between the electrostatic force and charge can be deduced from the graph? So if you look for the gradient, okay, we know that F over Q, which will be the same as F over Q, is the same as the electric field. People call it intensity. Okay, so electric field intensity. Let's just leave it as electric field. Then 8.4.2, use the information to calculate the magnitude of the electric field. Then they talk about it there. Okay, when it experiences a force of 0,05 newtons. Okay, so what I'm going to do, we know that the electric field is given as the force divided by the charge. So that's going to be 0.0005, 0.005 over the charge. In this case, it's 0.05 goes with a charge of 1. So 1 times 10 to the negative 6. Okay, when I divide that, this is 1 times 10 to the negative 6. I'm getting 5,000. Okay, this is Newton per watt per coulomb. So I use the same batteries used, and all the resistors are identical with resistance of 3 ohm each. The battery has EMF and internal resistance of unknown values. Voltmeter readings are indicated as we can see. Define power. So power is the rate at which work is done. Okay, rate at which work is done, or the rate of doing work. Rate of doing work. The 9.2 focuses on circuit A. What would 2 through R2? So one thing we know is that this is 2.4 amps. Okay, this current is flowing through these resistors, but they told us that each resistor is a 3 ohm resistor. Okay, we don't care about the 3. Okay, what we care about is that they are equal in magnitude, and for as long as they're equal in magnitude, which means even the current that is passing through them will be split into 2. So that's gonna be 1.2 amps. Okay, it's the same as 2.4 divided by 2. The 9.2.2, they're asking us for the power that is dissipated by both R2 and then R3. So I know that power is given as IV, okay, the voltage and then the current. So I know that the voltage across R2 and R3 is 3.6, but then the current that's going to pass through both of them, the total current is going to be the 2.4, because they are only having 2 parts. So it's going to be 2.4 multiplied by 3.6, which gives me 8.64 watts. You can use other approaches, okay, whereby you look at the individual power, okay, and even the power here, because we know the current is 1.2, 1.2, and then you just multiply it by 2 or you plus them together. You should be able to get the same answer. The 9.3 is using circuit B. They want us to get the energy, okay, used for resistor R1 if the current flows for 10 minutes. Now we know that these resistors are in series, okay? And for as long as they are in series, the current that is passing through them is technically the same. But then the voltage is going to be, I'll say equal. The voltage should be equal. Okay, so the voltage of R1 should be the same as the voltage of R2, same as the voltage of R3. But all the 3 voltages must give us the total voltage because they are in series. Reason as to why the voltage is equal is because we're talking about the same magnitude of resistance. So what I need to do, number 1, is for me to determine, okay, the voltage of R1. So the voltage of R1 is going to be 7.56. Okay, I'll divide it by 2. So 7.56 divided by 2, I'm getting a 3.78 volts. 3.78 volts. So if this is the voltage, for me to get the energy, okay, I should be able to get the current and the voltage. I'm just calculating the power technically, okay, and then the time being taken. So these 10 minutes need to be changed into seconds. So we're going to multiply this by 60 to give us 600. So my current is 1.26. My voltage is 3.78 multiplied by the 10 multiplied by the 60. So I'm ending up with 1, 2, 1, 2. We only have 2 zeros. Okay, so it's not going to be sufficient. 1.26 times 3.78 multiplied by 600. I'm getting 2857.68. Okay, this is energy. Né? It's going to be joules. And then 9.3.2, how would the current be affected if R1 burnt and was removed? Okay, how is the current affected? So the current is just going to increase. Okay, so we can say that removing R1, okay, will reduce the resistance. Okay, removing R1 reduces the resistance, thus the current will increase. We know that current and resistance are inversely proportional. Okay, so when the resistance decreases, the current must increase. Then 9.4, can we define what EMF is? So EMF is the same as electromotive force, but the definition of it is that it is the potential difference. Okay, it is the potential difference across a battery. Okay, across a battery when no current is flowing. The 9.5 resistor R1 is replaced by another new 3 ohm resistor. Calculate the value of the EMF and the internal resistance for the battery for circuit A and then circuit B. So we're going to solve this simultaneously, okay? So one thing we know, okay, let's state the facts that we know. That if this is a 3 and this is a 3, we know that the effective resistance in circuit number 1 or circuit A is going to be product over sum. So it's going to be 9/6 plus the 3. Okay, so that's going to be 18 plus 9, which is a 27. And then I'm dividing it by 6, which gives me a 4,5. How many marks is it? Okay. So this is 4,5 ohms. So this is the effective resistance for this one. Then 3 and 3 gives us 9 ohms. So that's the effective resistance for circuit B. Then we know that the formula for the EMF is given as current into a resistance external and resistance internal. So if I look at circuit A, my EMF is going to be equal to the current, which we said is 2.4. Okay, the effective is 4,5 plus R. Let's call this equation 1. Then let's look at the circuit B. Our EMF is going to be 1,26. We said 9 plus R. That is equation number 2. Then we solve the 2, equate both of them. 1 equivalent to 2. So 2,4, okay, let's do that. 4,5 plus R is equal to 1,26 into 9 plus R. So let's open up the brackets. We know that 4,5 multiplied by 2,4 gives us a 10,8 plus a 2,4 R. Then 1,26 multiplied by 9 is going to give us 11,34 plus 1,26 R. Let's collect the like terms. Okay, so 2,4R minus 1,26R should give us 11,34 minus 10,8. 2,4 minus 1,26, I'm getting 1,14R. Then 11,34 minus the 10.8, I'm getting 0,54. All right, so let me divide both sides by 1,14, 1,14. So what's our R? 1, we said 1,14. That gives me 0,47 ohms. It's fine, let me just leave it to 2 decimals. Okay, then for me to get the EMF, I can just replace it into one of the equations. So it will be 2,4 into 4,5 plus the 0,47. So 2,4 multiplied by 4,5 plus, we said 4,5 plus 0,47, which gives us 11,93 volts. Okay, 11,93 volts. So if, okay, I'm just saying if we had rounded off, did they tell us about rounding off? Internal resistance, no, they never told us. So if we were to round off, let's say these to approximately 0.5 ohms, then we were meant to get something like a 12 volts for the EMF, which is pretty reasonable. All right, guys, so that brings us to the end of this paper 1, okay? And I wish you all the best in your preparation for paper 2. Let's meet then. I sign out. Hello.